Many thanks to organizers and to you all for the exciting conference. Okay, maybe some presentations on strange radiation looks strange sometimes, so we'll see. Okay. As you understand, the strange radiation term has nothing to do with the strangeness of the elementary particles. The term was introduced for the first time more than 20 years ago by Leonid Rodskoyev. He found very strange tracks on the photoemulsion as a companion process with LANR by explosions of foils. This text appears not only photofilms, but on the surface of the other materials, but only on the surface. Sources of the strange radiations are very, very different. It's discharges, it's hot nickel hydrogen reactors, electrolysis, and so on. The same processes make LANR too. Here we can see examples of track. It's just several examples. A lot of them you can, lot of other works you can find in this item in literature. You can see that it's the same effect, the same pictures, and very important, strange radiation has biological effects. I don't know positive or negative to humans, but it's just two works here I presented, but it's many more exist work on this topic. And what the properties of the strange radiation text? They, of course, strange. Appears only on the surface on materials. Some of tracks are periodical. I will show you a lot of such tracks. And each periodical track has unique pattern. Tracks are usually combined into groups of identical tracks. One group per 1 centimeter squared. Mostly they appear near the LANR reactor, in a near zone about 20 centimeters. And this effect has huge variability in time. Example of group of identical tracks. So you can see here boomerang-like shape that repeated many times, more than times. It looks like when the cat scratches by clothes. Yes, we have a cat. Her name is Chucha. I asked her. She said, no, it's not me. It's true because she's younger than that picture. Another example, you can see many times of some shape like number 7. It's 40 and more times of such tracks. It's very unusual. Current research, we used as source of strange radiation reactor of Alexander Parkhomov based on incandescent lamps. Usually incandescent lamps 300 watts. Materials to catch tracks, we used ordinary DVD-R discs. We counting some of track lengths on every disk. And we using electronic atomic forces and optical microscopy to learn track structures. Typical exposition looks like that. The Alexander Pakov's reactor is very, very simple. Lamp is placed in quartz tube here. We use increased voltage, more than 300 volts, and it's cooled by circulating water here. And we placed several disks around. Here, after exposition takes about 1 week. Here we counting the total length of tracks in millimeters. You can see that just one disk 3, gains large number of tracks, other disks not. We gain some statistics, 9 expositions, more than 40 disks. You can hear that average total track length is about 1 meter length total per disk, only in the near zone near the reactors, less than 20 centimeters, and about 2 orders less in the far zone. It's just example, just one photo of the disks with extraordinary big count of tracks. Mostly the tracks are smooth ones. Here I see just one periodical track, and this disk gains about 15 meters of track overall, not centimeters, not millimeters, 15 meters tracks. So, examples of periodical tracks. It's optical microscopy. You can see that each periodical track have unique pattern, and within each period we can see this, and so on. The pattern is identical through the periods. You can see same images, so this detail is identical to this detail, but here, picture, this detail is identical to this, and so on. Atomic forces images, you can see some profiles. Here we have dip of about 1 microns and width of such structure about 30 microns. Same images, AFM images, note that these pictures are given from different periods. And you can see that they have identical structure in very, very fine details. One was a periodical track, length is about 5 millimeters, it's long. There is the questions, where the start and where the end of the track? I note that start is here, end is here, but is it true? Maybe vice versa. We measure the period of the track through the whole the track, and we found that through movement from bottom to top, period is changing. Here, it's bottom of the track, and the period is about 200 of microns, and it decreases while we go to top. Here 198, then 194, and then 189. So period is decreased, and we can assume that it decreased from start to end, because I assume that we see the traces of some rolling solid particles. Particle is destroying the surface of the material, and it maybe is deforming through its rolling, it destroying through its rolling itself. Another track, very interesting track, because we can see how the one solid particle on the right side divided into two particles through its track. So here it's two particles rolling. In more detail, you can see D, C images, continuous footprints. Here it's one particle rolling, and then it's separated, and we can see separated footprints to parallel tracks. And again, we can measure the period in the starting of the rolling this particle. It consists about 67 microns. And then when we see the two rolling particles, the period is decreased. 57, 52, 50, and so on. And another last periodical track for today. Breaking point. It's here point. This fracture is characteristic part of many tracks, not only periodical but smooth too. We can see that some solid, more bigger particle is rolling here. Here it's breakdown, it's divided into several particles, and they starting to move in the other direction here. And again, when we measure the period, we can see that here, when the particle was whole, the period is bigger than all the traces here when the particle breaks down. For example, 72 microns here, and 44, 45, 62, and so on here on this parallel tracks. So, what about characteristic size of periodical tracks? Period is about we measured from 20 to 200 microns, and we just divide it to P, and we get size of particles from 7 to 70 microns, if of course they not slide during rolling. But periodic tracks are very rare. We see on this material, on the polycarbonate, DVD-R discs, mostly smooth tracks. Here we can see some images, they're not so interesting, and AFM images show some structure. It's like smooth furrows, often going in parallel. Sometimes we can see, not sometimes, every time, we can see embossed material edged here, and it's just profiles here and here, two profiles. And we can estimate the particle size that slides here. About many than 10 microns, from 6 to 8 microns, some particle sliding here. Such tracks, of course, are possible only if some force is dragging solid particles on the surface. And we estimate the forces of the order of about 10 to minus 3 newtons per one particle. It's rather big forces. For comparison, the weight of such particle, if it consists from iron, will be 7 order less. And of course, through the movement of these particles, some work is done by the forces. And we can estimate this work about 10 to minus 6 joule per one track, several millimeters. And when it converted into head, we can find that the particle is head itself and heading itself and heading the surface too, up to many degrees, up to maybe 1000 degrees. And we can hypothesize what is the periodical track. When some bigger solid particles, about tenths of microns, is rolling around the surface, it destroys the forms and we can see some periodical track. What is a smooth tracks? When the particle is smaller, it has more heading due to less head capacity. And it's heading up to the melting point of the material. It's very soft material, about 300 degrees in polycarbonate, and then it just slide upon this melting material. So different is in size of particle. Of course, we have open questions. First, what's the nature of that solid particles? Another question, what's the nature of forces that press and dragging these particles upon the surface? Alexander Parkhomov knows the questions about the first two questions, but I have no time to speak about these answers. And another question, what do identical tracks mean? I don't know, and even Alexander Parkhomov doesn't know. Maybe nobody knows. And last question, what the relation of the strange radiation to Lennard? I'm afraid the answer will be only when we find out what the Lennard is. But what the Lennard is? Of course, cold fusion is the Lennard. It's low energy nuclear reaction. But Lennard is not only cold fusion. You can see that picture, you can see some black box here. Yeah? Maybe we don't understand what is inside. But when we put something in, we get anything out. Anything means whole periodic table and little bit more. Beside of unstable isotopes. It's very interesting, it's very important, and it's very good for our future without radioactive ashes. And a companion radiation here is strange radiation. Some answers what the black box is, you can find in this work. But I very like this picture. its authors of this presentation, and maybe not only of this presentation, we can hear that we see some miracles in the experiments. So conclusions. Tracks are formed by the movement of some solid particles with sizes of the order of microns or 10 of microns. We can determine the direction of particles' motion by precise measuring the period. The particle size and period decrease along the track. Particles are destroyed and deformed during this movement. The forces driving these particles along the surface are of order of 10 to -3 newtons, large forces. The movement of the particles under this action of external forces leads to heading of the surface along the track. By the way, it may contribute to excess head of length reactors. Why not? More smaller particles, micron-sized, are headed to high temperatures and lead to the melting of the surface material. This is how smooth tracks are formed. And the movement of the large particles, tens of microns, doesn't lead to melting, and periodical tracks are formed by rolling of such particles without melting surface material. Here are some items on literature. It's just a small part of literature. You can find some references in number 2 here. In the last picture, I like the idea that there is some new principle that is missed by physics. And when we find, we'll find such principle, we can understand what the lambda is, what the strange radiation is, and maybe something else. Thank you very much.
Thank you, Vladimir. I see we've got a queue for questions, but I have one. I'm going to use my privilege to sneak in first here. I noticed that in the images you showed us of tracks, right, that they all go to the left. Yeah. Can you think of a mechanism why they always go to the left? It can't be politics.
Not only to the left. It may you can turn the disc.
Okay, yes, absolutely, and then they're going. You flip the image, and they're going to the right, but they'll go the same way. Your boomerangs are all the same, and so on.
What is the question?
Well, the question is, why do they always veer in the same direction? Yeah.
I don't know.
Okay. Another mystery then. But thank you very much. I've always been a fan of Perovskayev's work, and for me the real mystery is how do those tiny particles stay so hot for so long? But, sorry, Bob?
Thank you, Alan. Thank you very much, Vlad, Bob Green at Martin Fleischmann Memorial Project. So I'm very happy that you credited Alexei in your last of your references there, because his work is an excellent addition to the study of these particles, or whatever they are. And also your SEM image that you shared from M. Solin from his 2001 direct electricity generation patent. He actually has a drawing of that same one in his 1992 patent, but it's not an SEM, but it's the same thing that he drew. I mentioned the Bogdanovich long-lived plasmoid paper. In there, he describes plasmoids forming crystal-like structures where these substructures rotate around their own axis and the overall crystal-like structure rotates and rolls on surfaces, and he's caught it on video. We actually published one observed in a water spark plug 2 years before he published that paper. And so we have observed these things as well. And it is the same as the buckyball-like form as the claimed form of coherent matter clusters as detailed in the drawing in the awarded Lockheed Martin's 2013 patent, Systems and Methods for Creating Coherent Matter Wave Beams. So they look equivalent. They have 6 or 5 type arrangements of the magnetic charges. And these structures would be consistent with the clusters of magnetic charges to which M. Solin ascribes nuclear reactions, including nucleon decay, in his awarded 1992 quantum coherent nuclear reactor patent. And in regards of why you see them moving along the surface, firstly, if their binding energy is much, much higher than ordinary matter, it leads to strange events in terms of interaction with matter. But what we have found is there is this disruption beam that comes out of the toroidal clusters, both out and in. And I believe I have shown on video where we have a toroidal cluster and it emits these coherent matter wave beams, and particles can be driven by that force that comes out. It's like a Caduceus spiral. So I think these things are explained. Yes, they are what causes LENR. There is much, much, much more that can be achieved with this understanding. So thank you, Vlad. You're absolutely on the money.
Thank you.
Hi, Mathieu Valette from the University of Szczecin. I have a question, maybe I missed the information, but are you using any sort of clean room protocol during your experiments? Do you manage the dust around? Because you have a cat, and having a cat is actually bringing a lot of dust everywhere around. So I'm just wondering, are you doing any of this? And if you would consider it?
We don't use dust or soot intentionally. And one of the explanation of what the particles are, Parhom says it's dust particle, but in very unusual conditions near the LEN reactors. Of course, in every room, in every laboratory, it's a lot of dust.
Yeah, that's why I'm suggesting eventually you to consider using a protocol of clean room management. This way you would have a very strong point about the case that would come from ambient dust just rolling on the surface of your disks.
Yes. We can't do it yet, but it will good idea.
Okay, interesting work. We in our experiment we usually use it before DC voltage polarization, and our detector. Thermal detector is covered by black mat. So this black mat is stable over time, maybe 2 months, 3 months, no problems. From about 5-6 months, we used pulsed current from the line, and this mat is easily damaged. So we don't know the reason, so we just observe it. And then we suspect something more, maybe thermal stress, but we don't have a real explanation. So what we want to suggest you to use a unipolar pulse to power the tungsten lamp, it's the same power, and to check if this effect is more strong or weak, I don't know. And moreover, it is possible to use the trick of dimmer, because you will have high frequency components in a very easy way, so to make some correlation about. Thank you.
Thank you.
Thanks for that talk, and I appreciated all the SEM and AFM images. My question is sort of simple. A clean room's great, but obviously very expensive. Have you run any control experiments where maybe you have a CD on the other side of the room, or a CD close to the reactor but flipped in the opposite direction, and then obviously have you done all of these SEM and optical microscope, optical micrographs of the surface of these CDs prior to any experiments?
We have not only experimental discs, but control discs too, of course. We put discs on the several meters from the reactors, and no tracks we have. Sometimes we put the discs one upon another, and just discs what surface is contact. It's go to air, yes, against the tracks. We have put the discs into the plastic box. We have no tracks then. It's very complicated picture, and very lot of work to do.
Thanks, that's really good to know. Thanks.
Thank you.
Well, thank you, Vladimir. If there is no other business, I suggest we break for coffee. And don't forget, you want my card too.